Well, thank you very much. I want to talk about where we were, where we're going, and I want to add in some personal reflections on that issue, mainly because that's what Linda asked us to do for this night session. So I'm Tom Herring. I'm a professor at geophysics. I went via Harvard University, did my PhD at MIT, and started in Australia at University of Queensland. Now, to start a geodetic program, you need atomic clocks. This is from 1952. The idea of the NIST atomic clocks, very dapper-looking young lad there. It's not me. So you need to combine clocks with the ability to measure distances electronically. This came out of the 1950s, radar developments in World War II, and these are examples of an instrument called a telluriometer, which is actually an X-band microwave system, and then geodemeter, which is an optical system. And we'll come back, and we need, not only that, but we also need artificial satellites. Sputnik, of course, is very famous in 1957, but amazingly, in 1959, the first transit satellite was launched to do navigation, just 2 years later. How did the tectonic world react to this? Well, in 1944, we had the Holmes paper on what drove tectonics, and that was based on Wagner's 1912 hypothesis that we had continental drift. Harry Hess in 1946 was doing that. We skip ahead to the 1965, Tuso Wilson giving a plate motion view at that point, which looks very similar to what we see contemporarily at the moment. And then we go to Jason Morgan, 1968, going across the mid-Atlantic ridge, giving us rates now which are running around 15 millimeters per year to 20 millimeters per year for that rate. This is in 1968. So plate tectonics at this point was being adopted as a theory. The geodetic community response to that was the Williamstown report. Byron Tapley talked about that last night. It's an amazing report if you ever read it. It costs $3 if you can buy it. It came up with 8 recommendations, but one of them specifically was to do measurements to 1 to 10 centimeter per year at the time we knew where things were within 10 meters. We developed VOBI. This is the Haystack Observatory, very famous. This is the Onslow Space Observatory, which we'll come back to in a second. And then we have satellite laser ranging, developed at Goddard. So where was I in all of this? Well, in 1976, I was going to university for free in Australia because I got good enough grades. And in fact, if you got really good grades, you had to get stipend paid, which was my case as well. But we had to work practice. So I was in Papua New Guinea, and it was hot and wet in that area. Next year, I went out to Mount Isa Mines. That's me again. And here, again, it was hot, wet, and dark. And I really decided that maybe research at MIT was not a bad way to expand my career. So that's where I went, arrived in 1979. 1981, we first published the report showing we could do actually sub-decimeter intercontinental distance measurement, a whole host of actors involved in doing this. And we had so few results, we actually tabulated every single measurement. 1986, we did the detection of plate tectonics, the 17 millimeter per year rate across the mid-Atlantic ridge between Haystack Observatory and Onslow, Sweden. And this was contemporary motion, and that was 16 years after the Williamstown. This is what we see to Onslow now. This is the GPS results, and that's just the linear trend. There's actually a discontinuity here for a radome change, and if we take out that linear trend over that 22-year period, this is what we see. This is a 3 millimeter scale, and interestingly, there is signal in that scale. There's an offset here due to a radome change. There's a processing change at that point. So this is where we are. What changed between 1986 and now? Well, we had UNAVCO formed in 1984, which Jeff's already spoken about. We had the SCUM group from JPL, USGS, and MIT in 1986, and we had the IGS starting to form. We went from large government programs to things driven by PIs, and I think that made a major difference. This is what we have now, high-rate GPS data. This is from the Maya-Chichapa earthquake, UNAVCO data. 300 seconds after the earthquake, we can still trace the GPS results relative to the accelerometers. This is where we're ultimately going. This scale now is down to 1/10 of a millimeter. This is one of the monument test results from UNAVCO. They're human hair. That is the scale of that figure. And so our penultimate accuracy. So where are we going? Well, we have geodetic imaging at incredibly high spatial resolution. We have high rate continuous data, tens of microns in accuracy. Where we go from here is really, I think, up to the young people that are in this audience. Me, personally, I think I'll just find a relaxing place to have a nice adult beverage. And actually, I think I might actually do that directly after this session. Thank you.